Module 6 covers everything on wireless. Uh, Wireless networking for home networks, uh, enterprise deployments, and even Internet of Things, IoT. IoT includes all those small devices to track sensors, temperature, movement. Your Nest at home is one of those IoT. Um, so it covers all that. The author decided to remove satellite communication and also cellular communication. I will cover a little bit of that in class, at least to introduce you so you're aware of it. I think it's good to know because that's more wireless communication on a larger scale, but it's still something good to know, you know, so when it comes time to talk about it. But module 6, here it comes. So we'll introduce wireless transmission, explain all the standards for 802.11. 802.11 is the standards for wireless. Remember that 802.3 it's the Ethernet, but 802.11 is wireless. How to plan a Wi-Fi network, how to secure it, and how to troubleshoot those networks. So wireless communication is basically has to obey the same rules as we do on a wire or as we do on fiber. The same layers, everything is the same. The only thing is we're using radio frequencies, we're using radio waves. Or layer 1 here, it's radio waves. The header on layer 3 is a little bit different. It has more information because now you got an access point in the middle to connect to your wire network. So we'll go into that, and also we'll see how the communication changes from wire to wireless and the challenges that you have with a wireless communication. So the wireless spectrum is the range of frequencies that you can use for data communication. That the spectrum ranges from 9 kilohertz all the way to 300 gigahertz. If you go to the book, chapter 6 at the beginning, there's a table that shows you all the different ranges of frequencies. Now, the FCC, the government, is the one that regulates which frequencies you can use for the different devices. Worldwide, they had to come out also with a standard to follow those rules. So when you buy an access point or any wireless that was produced in China or produced in Japan, whatever is produced or produced in the United States, they have the same ranges of frequencies. There are different standards, things vary. That's why sometimes you can buy, for example, a cell phone that is for T-Mobile, but when you try to put it into AT&T, they tell you, well, it doesn't really work too well on AT&T as it works on T-Mobile, and that's because T-Mobile owns some frequencies and they operate on those frequencies. And when you go to AT&T, they have their own frequencies, so the phone has to be capable of working on all those frequencies. So when you buy a phone that is unlocked, that is supposed to be used on any system, is because the phone is capable of working on all of those frequencies that all those companies are using. It doesn't support everything, but you have to make sure that those frequencies work. So that's why sometimes you might have a cell phone that you take it from, I don't know, AT&T to T-Mobile, for example, or Verizon, and you don't get all these speeds that you're supposed to get. That might be because there's one frequency that is missing. Locally on Wi-Fi, for networks, the standards are being set on the 2 gigahertz and the 5 gigahertz, right? And it was still within that spectrum. Now with the new Wi-Fi 6 or 6E, is using frequencies above the 5 gigahertz, so it's getting more into the 7 gigahertz. We looked at frequency before. Remember, the frequency is how fast that cycle goes up and down within a second. So how fast it oscillates. So of course 9 kilohertz is a very slow oscillation. 300 gigahertz is a very fast oscillation. So these oscillations, the signal goes up and down, carries information. So the more cycles you can have within 1 second, the more information you can cramp into that 1 second. Comparing from to 9 kilohertz. So you have devices like the RFID, is a radio frequency identification. Those are usually small devices, but the information that they hold is small. The data they can hold is like 1 to 8 kilobytes. It is very, very small information. It's more like a code or like an identifier. So that's why they used to identify devices, or track things, and all they do is put like a specific number, and then when you retrieve that number, that's all you need, nothing else. Your credit card, when you tap, remember when you tap to pay, basically you have an RFID in there. When you tap the device, it sends a signal, like a power signal. It powers the chip. It sends information back, everything that it has in one shot. Boom, 1 to 8 kilobytes of data. That's all you need. Data, especially numbers, is very easy to store. Right? We're not storing pictures or like music with sound, the digitized sound, anything like that. That it takes or voice. What they have inside RFID is just small information, numbers, just a set of numbers. It could be binary numbers, hexadecimal numbers, any kind of numbers, but the data is there, and as you get close to it, it will send information. NFC is similar to that. NFC is actually made for to carry more data and maintain a communication between the two devices. This works on the like 13, 14 megahertz. So now with the megahertz, you have more information that can be sent. But usually NFC is a near field communication. You have to have the devices really close to each other, kind of like you do with the RFID, that once they touch each other, one will send a signal to the other, and they establish the communication, they trust each other, and they start sending that. Some of these Samsung phones used to have that they have the NFC built in, so you can actually put two phones next to each other, and they start sending, I don't know, send pictures and things like that. But it is slow. It's not really fast communication. So this is an example of those even RFIDs or the NFC tags. It's just like a small fob, an FOB, and the information is stored inside a small chip, and they don't have any power. There's no batteries on these devices. Kind of like your credit card. You don't have a battery on your credit card. So the magnetic waves are induced into the device. Those magnetic waves produce a small amount of power, and that amount of power is sufficient to power up the circuit and start transmitting that signal. That's the job that they do. Once they receive power, they turn on, and then they send the signal right away. Sometimes that's when you need to tap two or three times. So you might have to like turn it around and all this until you get that induction into your device. Transformers usually work with an induction. When you have a transformer that changes your voltage from 110 to, I don't know, 110 volts to 12 volts. What it is inside is a coil on the 110 side. It generates electromagnetic field that gets induced into the other coil on the other side, and that coil is made in a way that once it receives that electromagnetic waves, it induces a voltage into it, producing the 12 volts. So imagine that second side, the left of that, on this RFID built in, or your credit card has a little coil, and it catches a signal, powers up, sends a signal, done. Now SigWave is similar. It's just to transmit data, but SigWave has capabilities to go more like 100 meters. So now here you can have sensors around your home, sensors on your business, that they can communicate across larger distances. So SigWave are usually powered by small batteries, small sensor you put with batteries, so it has its own adapter, and those are like more for like permanent, the devices. SigWave needs to have a hub. The hub is the one that controls everything, so you can use it as as a central point to control all the other devices. Zigbee is similar. Zigbee is also used for a lot of sensors, especially on our air conditioning and other IoT devices. Remember now everything's IoT. IoT is, like I said, is Internet of Things. It just small devices for small purposes. So chances are, if you have, I don't know, a microwave or your washing machine or something like that, some of those devices, they're IoT devices. They might use Zigbee, one of these protocols, in order to be controlled. Then we're all familiar with Bluetooth. If you have a cell phone, most likely you have a Bluetooth device, either your headphones, you may have a speaker. You can connect to your car through Bluetooth. There's all kinds of different Bluetooth devices. Bluetooth is still is an IEEE standard, 802.15.1, something like that. But Bluetooth operates now at 2.4 gigahertz, and 2.4 gigahertz gives it more speed, more data transmission. So that's why you can send audio to your headphones. There's a little delay there, but you'll get that audio on your headphones, and it's clear. You can have the whole audio spectrum. When you talk on your phone, it will transmit voice and audio at the same time. So but Bluetooth is very ratified. Has been used for many years. It was gone through a lot of revisions. So you got a Bluetooth 1.0, 2.0, 2 point something. There was a 3.0. Then we got into 4. We got into the 5s, and I think the latest Bluetooth is 5.3. That and every time, of course, it creates more enhancements, more energy efficient, to save power, more capabilities to connect with other devices. And Bluetooth also, it depends on how much power they introduce to Bluetooth to the device. Then you'll get different ranges of distances. Your smartwatch connects through Bluetooth, and sometimes you can walk away 20 30 feet away from your phone and you can still get those messages. But yet sometimes you can buy some cheap headphones and you have it right, your phone is right on your pocket, and they won't reach all the way to your ears because the distance too far, or something, the body starts interfering with the signal, something like that. I did have an MP3 player that was like that. It was like meant to, I don't know, be using your collar or something like that, because that was the only way that can get the small Bluetooth music player to get to the headphones. So it depends on that, on the power they introduce, but they vary on this, and they're not all the same. And also it depends on which Bluetooth standard you're using. That's the capabilities that you're going to have. ANT plus is pronounced just like that, ANT, A-N-T plus. That is more for ad hoc devices, something like direct devices, 2.4 gigahertz also. That protocol is owned by Garmin. So Garmin has a whole set of sensors for heart rate sensors and things like that you can have on you, or sensors that you can have on your bicycle, all kinds of different things. Those are transmitted through the ANT technology. But it's similar to Bluetooth. It's just that it's a proprietary, owned by Garmin communication. Also operating at 2.4 gigahertz. Infrared is a completely different animal. This one, infrared is it's a light communication. It's not a radio communication like all the others, like Bluetooth or Zigbee or ANT plus or any of those. Infrared is a light that is invisible to the human eye, right? So it's just below that, so you cannot see it. But it's usually for some kind of sensors, proximity devices, but mostly used on remote controls. And that's why when you have your remote control for your TV, you have to point to your TV. If you point to the wall, to point backwards, the little light LED, the infrared LED that is on the front of your remote, that it may have like a little black window, the signal has to come from there and it's directional. So it needs what is called a line of sight. Line of sight is that the sender and the receiver need to be completely in front of each other with nothing in the middle. Or with the infrared, you also have seen that if you walk away too far, it won't work. Some of the mostly remote controls for projectors, TVs, anything that uses remote controls to uses that. One trick, if you have a cell phone and you turn on your camera and you point to the camera to take a picture, let's say, of the your remote control, when you press the buttons, you will see those lights. Because with the naked eye, you cannot see it, but the camera can capture those things. And when you press the button, you'll see. So that's a way to check if a remote control that's infrared is working or not, is by seeing that. I know there's some devices like the Fire Stick from Amazon. Those they use, I think they use Bluetooth to communicate with the Fire Stick. So you will not see an LED on those. It's actually a radio communication. So that one you don't really need to point. You just need to lift it up because it's more like an antenna to make sure that they get the signal. This is not a pointing thing. You don't have to point to the device as you do on the infrareds. So this is the wireless spectrum as defined by the FCC. You see in the lower range you had the RFID, right above the below the 1 megahertz you have the AM radio. NFC is like in the 10 megahertz, so you have a better frequency. The same thing with Zigway, they're close to the FM signal. FM is like around 100 megahertz, and it goes on like that. So you got cellular, and then you got your Wi-Fi, which is at 2.4, and also at the 5 gigahertz. Right, the satellite communication, the C-band satellites also use that. Usually, like DirecTV and some of those services will use the KU bands. The K bands are above the 10 gigahertz, and those are just for satellite communication. So that's how they spread out, and these are just to create a standard so people can buy a device in anywhere in the world and make sure that it works. So you want to buy a radio station, it sends a signal on a specific frequency, and you make sure that your device is going to work with that. If you see, if you look at your radio, if anybody still listens to radio broadcasts, all the radio stations are between 88 and 108 megahertz, and they tell you there, 1035 is 103.5 megahertz, 103.5. I don't know. 91.3. If you notice also on the FM, this is something just has nothing to do with the Network Plus, but the channel separation, there's always a channel separation between radio signals. That channel separation ensures that a person can send signals on a specific frequency, that it doesn't overlap with the next frequency. So it's always a channel separation. So for example, something that you can probably relate to, look at your FM radio. Try to see if you can find, which you'll never find, a radio station at 100.2. It doesn't exist. You have 100.1 and it jumps to 100.3, 100.5, 100.7, 100.9, and so on. There's a 200 kilohertz separation in the channels in FM radio. So it makes to make sure that one radio station does not overlap with another one. So there's like some separation between the two. The separation between AM radio, I think, is 10 kilohertz. So that goes from 540 to 550, 560. And those, you see, they're all the even numbers because it goes every 10 kilohertz. Whereas FM radio starts at 88.1, and then you got 88.3, 88.5, 88.7, and like that. So it's a channel separation. Now, just like at AM or FM radio, that you have multiple frequencies for multiple radio stations and they don't affect with each other, wireless also have multiple channels. And the only way to control that is through channel management. You have to manage those channels to make sure that one user does not interfere with another user. So for the wireless devices, you'll use either a frequency hopping, spread the spectrum, which what it will do, it will send some information on one frequency, and then it will hop to another frequency to send the next information, then it will hop to another frequency. So that way you use multiple frequencies, multiple pieces of frequencies within that spectrum to communicate data constantly. And then the direct sequence spread spectrum is the one that will take like a whole set of frequencies and mix them together and then send on all of those. So this frequencies are broken up. It depends on the usage. So that's what you have for the Wi-Fi that uses the direct sequence. Bluetooth uses frequency hopping, and Zigbee uses the direct sequence also. So it depends on which technology you're using. It will use different methods to do the channel management. Okay, now to transmit these signals, you need to use an antenna to send and to receive, right? Antenna's design is a whole area of studies to create the antennas, and the antennas also needs to match in order to send and receive the signal. So if you want to communicate with a specific frequency, the antenna needs to be designed to send on that frequency and also to receive on that frequency, so you can communicate with each other. If you remember the old days when you had those aerial TV antennas that they were made of a whole bunch of like little spikes or bars, and they'll have a long one, then a shorter one, all the way to the front, is because each of those bars will pick up different frequencies. So each bar was made to receive different frequencies so you can get multiple channels. So that was because your TV was supposed to get multiple channels. But when you're on Wi-Fi, basically you need to pick up just the signal for the Wi-Fi, either 2.4 or the 5 gigahertz, or now the 6-7 gigahertz if you have Wi-Fi 6. Wi-Fi 6 being the new standard with faster speeds. So, and then when the antenna sends a signal, it creates a radiation pattern. That radiation pattern is the one that shows you how the signal is being spread out through the air. I have one of the links on your Blackboard that shows you a document from Cisco that is a little bit long, but it shows you everything, how the antennas, the pattern shows you how the antennas are. It's a three-dimensional pattern, because remember it's over the air, so we're not talking just X, Y, we're also talking about Z. So it might create like a bubble. So it goes in all directions, and but that depends on the design of the antenna. So you can have directional antennas, or it's called unidirectional, that it goes only on a single direction. That's like if you want to have like a point-to-point. So you have one location, let's say one building to another building, and you want to connect the two through wireless because there's no way to get I don't know, fiber or cable, something like that. Happens to us at Miami-Dade a long time ago with one of the campuses, that there were two separate a building that they acquired, but there were no interconnections, conduits or manholes on the ground facilities to connect the two buildings together. So the immediate solution was to put antennas on both sides and communicate like that. Back then, they will give you a 54 megs, which a lot of the computers used to connect at 100. So 54 was not, perfect, but it will give you something that was usable, and they could have computers in the meantime while we get, the infrastructure to connect the two buildings together. So that's where you use a directional antenna. Or you can have the omnidirectional antenna. The omnidirectional antenna that's the one that creates more like a bubble around the antenna, and it actually propagates on all directions. It goes on your plane, all around it, and then even up to the ceiling, more like I said, like a half a bubble on top of the antenna. Okay. Depends on where the antenna are. That's when it's going to determine your range of signal, how the antenna is built, what type of antenna it is, and also how much power you send into it. It will depend. It will define how far the antenna is going to go. So based on that pattern, the radiation pattern, that's to see where the antenna is going to propagate, on which direction it's going to go. If you have the point-to-point, you have what's called the line of sight. Line of sight is when you actually can see it. So if you're in a classroom and you have an access point right inside the room, you actually have line of sight. Your device can see directly. If you create a line between your device and the access point, you can draw a straight line between the two, and there's nothing in the middle. Now, if the access point is in the next room, like we have in our classroom, our classroom is on 8216, the access point is on 8217, this is the other classroom, so that is not a line of sight because it has to travel through walls and all these things, and it changes the signal. Okay, the signals usually don't go on a straight line. The signals bounce all over the place. When you propagate a signal, the device will blast radio waves all around it based on that pattern again, and that signal is going to bounce from different places. So sometimes what you get is a reflection of that. But that reflection, it depends on the wall, the materials, and things like that. It can be affected. So sometimes it gets deflected, so you get like a delay, or sometimes it's absorbed by the object and you lose some signal, and I will go through some of those. So one of the first effect you'll get on this is called the attenuation. Attenuation is when the signal starts to lose power because of distance mainly. You know, when you start like getting too far away from your source of the signal. These signals, of course, they're not meant to go by miles. It's usually by a radius of like um, I would say 25, 50 feet. Once you get 100 feet, then you start losing the signal. So that's called attenuation, where you start, losing your signal. Now you have also fading, which is caused by the signal fading, going into obstacles, and the energy starts to fade, and you start dropping the connection. Like even if it goes through a wall that is not a metal or concrete wall, it will go across, it will go through the wall, but it will fade out. Uh, Also, you might get interference. Usually, you get interference from electromagnetic waves. Microwaves will generate a lot of interference on Wi-Fi. On other motors also generates a lot of EMF. So that affects your Wi-Fi. So there's a measurement called signal to noise ratio, the SNR, and the SNR is also what determines how good of a clean signal you get. So signal to noise ratio is a ratio. Remember, ratio from mathematics is a division. So you take the number the number at the top is the amount of signal that you get. The number at the bottom will be the amount of noise that you get. And when you make that division, it gives you a ratio, which is called the signal to noise ratio. Simple as that. But you have to measure the signal, measure the amount of noise. So hopefully, obviously, you want to have less noise than the signal, so that way you get more signal. But if the noise is too large, when you go the signal against the noise, then the noise just propagates, it actually affects your signal, and you won't be able to get that signal. This are some other terms that if you work with Wi-Fi, you need to remember this just so you can explain, and what's happening on some of the problems that you get on the wireless coverage. Refraction, it's just when the signal goes through an object and it changes direction, is diffracted. Remember that diffraction is kind of like when you put a pencil on a glass of water, and when you see it, the pencil looks like what's in the water is moved, right? So that's a refraction. So that happens with wireless signals. When it goes through certain mediums, it will refract the signal. Then you got a reflection. Reflection is just like the word says, reflection, like on a mirror, right? That it will bounce back, and it goes into an object, and it bounces back towards the source, or on a different direction. If it hits on a perfect angle, of course it will come back to signal. If it hits that reflection point in an angle, they will reflect back on the same angle, but it will just change directions. Scattering is another a phenomenon that you get on wireless, but scattering is more like when you go through trees or some objects that they're kind of a little bit more dense, but they won't block the signal. So when it goes into objects like that, it will scatter the signal. So it will send it to different places. Now, diffraction is a little bit different, because diffraction is when you hit an object that it might be kind of sharp, like on a corner of a building, a corner of a table. And what it does is that it diffracts the signal. It will split it into multiple waves. a little bit different from scattering, because scattering also goes in different directions, but scattering is more like goes in and it goes in all kind of different directions. The diffraction can be predicted, because the diffraction, if you know the surface and the roughness of the surface and the shape of that surface, then you can predict how the diffraction is going to go and how many split signals you're going to get. So because of all this refraction, reflection, scattering, and diffraction, you create what's called multiple path. Multiple path is a whole area of studies. I did some papers on that back in my days in school on multipath signaling. Because when you are sitting in an area, even though you have line of sight to your device, you get multipath signals. You get all these signals bouncing from everywhere that still reach your receiver part, your phone or your laptop or your wireless device. It will still receive it, but they'll come back at different power, at different delays, and they come at different times with different strengths. This is very, very clear when you do telephony for cellular telephony, because you're in the car, there are hundreds of buildings, there are all kinds of objects there, buildings to diffract your signal, there are trees to scatter the signal, and there are some surfaces like glass and things like that, they will reflect the signal. So you get all of this getting into your device. That's why I was surprised that telephony was taken out of the this chapter, but it helps explain a lot of what happens on your Wi-Fi signals. So the book has this representation here. Like if you have an access point, a small with omnidirectional antennas, these are omnidirectional, so they go in all directions. So you get some reflection from the ceiling, you get some diffraction when it goes through the walls, and also from when I hit the corner of the table. Now, when it gets a plant or something, it gets a scatter, so you get all those signals bouncing back and forth. So that's why you can have a laptop and move it around a room, and you might move it to a few feet left or right or the front to the back, and then you start to get a better signal, just because on that point where you are, you get a better reception. Now, at one point, laptops normally nowadays, laptops have their antenna built around your LCD screen. So you have the LCD screen, and then there is like a wire, basically like an antenna wire, that goes all around the screen. It's like a loop all around that, and that's where your antenna is. And so sometimes what you need, all you need to do is to kind of flip your screen a little bit, tilt it a little more, or move your laptop left and right, like rotate it left or right, to get that antenna receiver at a different position to see if you can get a better signal. So like I said, sometimes even if you're on a desk in your classroom, you have this laptop right in front of you, if you get a good signal, you can just tilt it a little bit to the left or to the right, and that might improve your signal just because of the position where your receiver antenna is at. So like I said at the beginning, 802.11, the wireless supports just the same layers as OSI. And since this is a medium, it works on layer 1 and also has some layer 2 protocols that works on the Wi-Fi. So that's refers to Wi-Fi for wireless fidelity, but it's a wireless LAN. Some of the standards, some of the older standards is 802.11b, and then it went to the 8 radios. I think those were the 5 gigahertz. Then G increased the speed a little more. I think if G will give you the 54 megs, and then 802.11n gave you more speed. Then the AC, which was another wave of radios, until the latest one that we're doing the 802.11ax, that it gives you also higher speeds and more, more throughput. The AX operates on the 2.4 and 5 gigahertz. That can give you a throughput of 9.6 gigahertz at optimum performance. It's not you're going to get all that, but you can get up to that. The AC was the older one that works at the 5 gigahertz, and that it depends on which. There was a different designs, the wave 1, wave 2, wave 1, wave 2, and wave 3. And each one, it just increased the speed. It went from 1 point something to like 3 gigahertz, and then it went to 6 gigahertz, almost 7. And now the AX is the one that, because it's using 2.4 or 5, or both at the same time, it can give you a faster speeds. And also AX is using the 6 gigahertz channel, which was just released by the FCC, so you can use the Wi-Fi 6 and improve the communication. All the other ones, there was a standard. Was you see sometimes on your computers, I'll say that it supports BG and N. BG, it was like I said, the older ones that they work on 2.4 gigahertz, and the N worked at 5 gigahertz. So it just how things are um, designed on your device, if it's a legacy device or a new device. I know some of the new laptops actually come with AEX network cards. The LLC is a link layer control protocol. Sublayer is the one that allows multiplexing. Remember, we talked about multiplexing when you got multiple signals mixed into one, right? And LLC also provides flow and error control and reliability. Now you have to do multiplexing because now you got multiple users. An access point can handle 40, 50, even 100 users simultaneously at different frequencies and at different protocols. So the access point is able to do multiplexing to mix all those signals into one, communicate with your network, and then bring everything back to every device at the right frequency with the right protocol. So I'm glad that the book is now introducing more new technologies. The old book, I guess it was just getting too old, but there's new standards that were brought up in the last, I would say 5 years, 5 to 10 years. You can do now what is called channel bundling. Each wireless channel uses 20 megahertz per channel. And when you do channel bundling, you can join those two megahertz, the 20 megahertz to make a 40 megahertz, and now some of them even support the 80 megahertz on the Wi-Fi 6. But by doing the channel bundling, now you can have all those channels in the middle, and like I said, each channel is kind of like a radio station, so it's kind of like listening to 40 radio stations at the same time. So imagine the amount of data you can get, right? In a way, to me, it's cheating on the design, because what you're doing is bonding things together to make it faster. So kind of like saying, oh, let me give you a pipe of 1 inch and you get a certain amount of water or some throughput through that, but I want to make it better. I want to put 4. I'm going to quadruple your speed. It's like, well, of course you do. You're just giving me the same, but 4 times. So it's just now that me being able to use only 1, I can use 4 at the same time. So that's when you have the MIMO, the multiple input, multiple output. So rather than using just 1 pipe, now I can use 4 at the same time. I can send and receive at the 4 simultaneously. So that gives me, more throughput, but it's just because I'm adding more, pipes together, right? Multiple inputs, multiple outputs at the same time. And that's possible with the channel bundling, because now, right, having, like I said, the 20 megahertz, I can get 40, I can even get 80 megahertz and do multiple channels. And then you have what's called the multi-user MIMO or MIMO, where you have multiple in, multiple out, but for multiple users. So you can have multiple users doing exactly the same channel bundling, but for a lot of users. And that also depends on your antennas. It depends on the design. It depends on all other things. But the multiple use MIMO, it is available on the Wave 2 devices and up. Remember, after that, there was the Wave 3 devices. That's part of the 802.11ac. And then everything beyond that, AX, the new Wi-Fi 6, it will use the same technologies. So as technology changes, you get more things. So now with the Wi-Fi 6, which is the AX devices, introduces the orthogonal frequency division multiple access. I'm not going to go too much into the details, but it's the way that they do is pretty amazing. What orthogonal does is that takes your 20 megahertz channel. Remember, we talked about the 20 channel bundle. You get 40, you can get 80. it takes that 20 megahertz channel and it will divide it into smaller little pieces of frequencies and allow you to use those small little frequencies. And by doing that, it gives you, by giving you those small pieces, you get a whole bunch of little channels that you can use all at the same time, and that helps for the multiple users being served at the same time. So that's why you get the multiple access, and that provides a more efficient communication, and that's when they're able to get into the higher throughput of the gigahertz, so the 1, 2, or I mean it's supposed to go up to 9, but 9 point something, but like I said, uh, uh, at optimum scenarios. But the orthogonal came in and introduced like a better performance on the Wi-Fi. It's funny because all of these frequency divisions existed for many years. Even when I went to college and I studied radio signals, I remember studying all these frequency hopping and frequency orthogonal frequencies and stuff like that. But they were never applied to Wi-Fi. So now that there was the need to improve it, to make it better, because there's more devices, more implementation, more things are going that way, the engineers is like, hey, we got this that we can use on that and make it better, and let's use it, right? Also, you can have the frame aggregation that it combines multiple frames into one larger frame. So it's kind of like similar to doing jumbo frames on layer 2. Remember that we talk about the MTU, the maximum transmission unit, that is 1500. So each frame has to have that size of data. But if you're transferring largest amounts of data like backups and things like that, you can use jumbo frames. So here, what you use is the frame aggregation. So you can do something similar with the AMSDU, the aggregation MAC service data unit, or the AMPDU, which is aggregation MAC protocol data unit. So it's different ways to doing it that we're not going to get too much into the details of that, but it's a way that they did to improve the communication. So this is how the MSDU works and the MPDU. The MSDU on top, you see that now you have 3 payloads into one packet, and it just puts the header and the frame checking sequence at the end. The frame checking sequence, yeah, just to check that the sequence is correct, and then the protocol PDU introduces one frame check and a header for every payload. So it's a little bit bigger, but because you have more frame checking, but improves quality because now every payload is being checked individually, not like putting a general frame check for 3 payloads at a time. So it depends on what you're transmitting, depends on what the information is being sent, is the technology is going to be used. This is all behind the scenes. I mean, this is not something you need to adjust or something that you need to configure or anything like that, but it's something that if you're going to do a packet capture, you're going to be seeing these things. So when you see it, you can get to recognize that which aggregation is using for the communication. Now, 802.11 also uses MAC services for the media access control. But here, just like in layer 2, that you want to make sure that the communication channel is open for you to transmit. Wireless cannot communicate all at the same time. It's not designed for simultaneous transmit and receive at the same time. So it's using more like you remember the full duplex, half duplex, can you send and receive at the same time, where you can send and receive. So that's what the problem that we have on 802.11. So the method that they use is CSMA. It carry sense multiple access, and then it's combined with the collision avoidance, which is a method to say, okay, if the channel is busy right now, then I'm going to back out to avoid a collision. But by checking that channels, if the channel is in use, then that's the carry sense multiple access to say, okay, is somebody using this channel? Yes, okay, let me try it on the next channel. Let me try on the next channel. Then I'll find a channel that is open so I can transmit on that one. And then once I grab a channel that is open, then I'll do the collision avoidance to make sure to see if I can send information through it. So all of this is going through acknowledgements, ACKs, ACKs. to see if the channel is open, and that puts a little bit more overhead. It also, what they use is the RTS CTS, which is clear to send, request to send and clear to send, which is an all also way of doing things. This is back in over like 20 years ago when they were doing serial communication through a wire, that they used a RTS and CTS to see if am I clear to talk now? Did you finish talking? Are you done talking? Okay, if you're done, now I can send my signal. So you have to request to send, and then you receive back a clear to send saying, okay, I'm done sending. I'm listening right now, and I'm ready to listen to you. So if I get that request to send, but I finish talking, say, yeah, sure, clear to send. Just send me the information. And the other end, when it needs to reply back, it will do the same thing. So have you done talking? Have you done talking? So okay, I can request to send, and then I get back a clear to send to, just reply back to my sending device. Like I said, this is all in the background. There's things that you need to see, need to know, because when you get problems, then if you get collisions, any type of collisions on your captures, and when you're troubleshooting, it is part of this CSMA C8 that is not working correctly. So this is more how the transmission works. You check for transmission, and it checks for activity. If there's no activities, then I can pause, and then it starts sending the transmission. If there's activity on the system, so it's yes, I pause for a brief pause. I mean, we're talking milliseconds. So I'll press for a few milliseconds, and then I'll check the transmission again to see if the channel is clear. Now, when you turn on a device on any Wi-Fi network, the first thing you need to do is to associate with that network. So when you open your laptop and you see there's multiple SSIDs, MDC Open, MDC Secure, MDC Student, you see those there, and you pick one. So when you pick one, let's say we pick MDC Open, the first thing that your device will do is to associate with that SSID and kind of get accepted, and you start getting all kinds of communications to get an IP address. You need to authenticate, you get authenticated and all that. But to get all that communication going, there's two things that you need to have there. There's a probe that is sent by your device, and there's a beacon that is sent by the access point. The probe is an active scanning. Is the device itself going out and said, hey, what the wireless channels are out there, how many SSIDs, the service set identifier are there that I can connect to, and then once you find one, then you can connect to it, or the passive scanning, which is the other way that the wireless device, your access point, sends that beacon frame, and it starts sending like a beacon, like a lighthouse that is sending the light. It goes, hey, I'm here, I'm here, I'm here, I'm here. So your device will pick it up, and it would you can associate with it, but you associate to that specific SSID. The SSID, it's part of that beacon information, right? And it's configured on your device. You can actually have it turned off if you want to. You can turn off the broadcast or your SSID and have some hidden SSIDs if you want to call it that way. But have you seen sometimes when you turn on your laptop or your phone and you start to connect to Wi-Fi and you see a whole bunch of devices? What's fun is to turn it on, do it in the in a shopping mall, where some of the stores have their own Wi-Fi, and you see all of these stores with the Wi-Fi. Most likely they have a password on it or something like that. It's not open for the regular users, But you'll see, and what you're seeing there is that beacon, either that beacon that they receive directly from the AP, containing information with the SSID, the service set identifier, which again is unique and is case sensitive. So if it's with capitals and lower cases, then it has to match, or is found by your device when it does the probe. Okay. On the SSIDs, remember, that it has to be case sensitive. So if you have an SSID that is hidden, that you don't broadcast that name and you want users to connect to it, you have to give exactly how the SSID is spelled. So if it's a dash or anything in the middle, any characters like that, then so it's there and it matches, so your device can actually associate with it. Now, from here, there's two terms that you need to remember, your BSS and your ESS and what they are. The basic service set, it's a group of workstation share the same access point. So if I have 15 or 20 users connected to the MDC student wireless, right? All of those are part of the same BSS, the same basic service set. Okay, now that's for the devices connected to one access point. Now the ESS, the extended service set, is the one sent by your LAN network, and that's a collection of access points that they all interact with each other. So these are all these access points that belong to the same network. Usually they are controlled by a wireless controller. I can show you that. I'm going to show you that in class with the wireless controller for the college. But they share the same ESS ID that to show that they're all part of the same ESS. So it is all these access points that belong to one network. You know, this could be a mesh where they're all in different places, but they're all working together. Whereas the BSS, the basic service set, is you and all the other users sharing the same access point on the same SSID. The independent basic rate set is something, if to use ad hoc technology, ad hoc is just connecting one to one, like a point to point. So that's me connecting to another laptop. We can create an IBSS and have our own short wireless between the two, not shared by anybody, not controlled by anybody, and then just between two devices. And that works sometimes to some devices that you want to connect to your laptop, or devices to connect to your phone. Remember, the phone is using Wi-Fi. It has a Wi-Fi radio in there. Besides your data is also the Wi-Fi. So when I said Wi-Fi devices, it could be your laptop, your phone, your tablets, all those, they work within any Wi-Fi network. So you can create your own IBSS for devices within your own device. And sometimes when you get some of those IoT devices, even like a light switch on the wall, one of those light switches they can control with your network. The first thing that they do is that sometimes they have their own SSID, and just to communicate with the device and then receive information of your internal network or your home network. Once it gets that information, it will reboot, and then it will try to join that network with information that you give them. If you give them the password and the SSID that needs to connect to, then that device will connect that. But initially, in order to connect to the network, it would create an ad hoc between that light switch that is wireless and your laptop or your phone, make the connection, and then receive the instructions that it needs so it can configure itself. So here you can see better what it is. See how you have a BSS is a set of devices within this, all sharing the same access point. So all those become a BSS, and the ESS, the extended service set, is the collection of all those three access points that are working together. Now we're getting more into the more meaty part of the 82.11 frames. So here, there are three frames that you have to be concerned with, which is management frames that are used for the association and reassociation. Remember, associations when you join a wireless network. Then you have your control frames, which is all this the CDMA to carrier sense. To control that communication with the request to send and the clear to send your acknowledgements, and also your data frames between the workstations. Okay, and here notice the difference between a regular Ethernet frame and your 82.11 data frame. See at the bottom says 82.3. 82.3 is the Ethernet. 82.11 has everything to do with the wireless. On the Ethernet, you have your source and destination address. Source address is your device, and the destination address is who you want to connect to. Now, the 802.11 has 4 addresses: address 1, address 2, address 3, and address 4, which are the address of your access point, because now you have the access point and the connecting point in the middle. So it's not just your source and destination, but you also have the 2 addresses in the middle, which is your access point acting as a middleman to get that communication. So you still have your frame check sequence, the FCS, on both them. The data, it's there, right? But you also have your frame control at the beginning and the sequence control to make sure that those data frames are delivered and received on the same matter in your communication. But the main difference here is those 4 addresses that your 802.11 frame would have. This is something new in the book also, that it describes some of the design for small wireless LANs, or how to configure access points and larger networks. This was not included in the previous revisions of this book. So if you want to install wireless on a small office or a home network, or the small office called the SOHO, the small office home office, right? The SOHO network. Most likely you have just one access point, right? It's the one that comes with either your AT&T router or your Comcast device, or if you might just put your own. If you just have internet from your provider, then you want to provide your own wireless. So that small device combines everything. It's a multi a purpose device that has an AP built in. It does switching, because you can connect devices at the back of the device of your device provided by the provider, and also does routing, because routing is what it connects you from your home network to the outside network. Remember that switching is just within your LAN, which is your own network, but once you get out of your LAN, you need a router. So those devices would have a router built in, which is your gateway to get outside. Most likely it will have the 192.168.1. something, and it could be, if your Comcast, it will be 1.1. If AT&T will be 192.168.1.254 or something like that, if you haven't changed it. But those devices will have that. Now, are you going to support IoT devices? Do you need that in your home or office? IoT devices, meaning all kind of different home devices to control the lights, control this, control sensors, different things that you can have in there. Smart speakers, thermostat, doorbells, cameras, refrigerators, anything there. Now everything has. I do have in my bathroom, I put a air extractor, the little fan for air extractor, that it actually came with an LED light, and also came with Bluetooth. So that Bluetooth can get connected to my phone, and I can transmit music while I'm in the bath or something like that. I can put some light music or whatever, anything that I want there. And also the lights can be connected to your wireless network. So now you can tell your Alexa or your Zigbee hub, it says, hey, turn on, or from my phone with an application on my phone, that I can tell them, turn on the lights, dim the lights, keep them on for like 5 minutes, put them on a timer, or anything like that. So all of those can be defined on a small network. So this depends also on your distance, the number of obstacles, meaning your walls and anything that is there. Are you on a one-story location, a two-story location? What coverage you want, what interference you're getting, right? Coverage, it means that you want to cover just the bedrooms or in a house, or if it's an office, you want to cover just the office area. What if you have like a warehouse, or you have like a storage? Do you want to cover wireless there? If you have a restaurant, there's a freezer, you might want to have a temperature sensor there to keep track of the devices there. I mean the temperature on the cooler. So it depends on what you're going to have. So of course, if you have a larger area, you might require multiple access points. For multiple access points, what they recommend to do is to do like a survey. Survey is basically you determine where is the best location for those access points. As a rule of thumb, you cannot have two access points too close to each other. If they're working together, what happens is that they are aware of each other. So what they're programmed to do is to lower the signal, both of them, so they don't interfere with each other. So if you put two access points too close to each other, they will fight with each other for that signal and they will power down. So now your coverage gets reduced. So in a classroom environment, if I want to have two access points, I'm not going to put the two access points right by the professor's or the front blackboard. I'm not going to put it close to the board in front of the class because the students are going to be sitting in the middle of the room and the back of the room. So most likely what I want is to have one at the front, one at the back, and not even both in the middle. I might just go what's called like catty corner, one in one corner, one in the opposite corner, right across from one corner to another. So you have those signal spread out. The two devices, they don't fight with each other, and then they will provide you with a full speed. So now students that sit on the front to one side of the room will connect to that one access point, whereas the ones that are close to the opposite corner and the back of the room, or everybody in the back of the room, it will connect to that access point. So now you spread out your load within the access points. The same thing if you have an office environment, you might have a conference room and you have office areas. Office area, of course, is less populated because in a big area, you might have like 4, 5, 6 people. Whereas when you have a conference room, you can have all those 6 people or 8 people or 10 people in the same room at the same time. So there you want to provide more density. There's two things that you can have: coverage and density. Coverage is, can I cover all the area? Can I go to every corner of this building and get Wi-Fi? And the density is, okay, I have 100 employees, can all come in on the one room and connect all at the same time, or they need to spread out through the whole floor, so I can have 40 in one corner, 40 in another, 20 here, 20 there, and then spread them out so you can have that density in each area. So yeah, this is part of the designs. If you have the blueprints of your office, it makes life a lot easier because the blueprint sometimes it shows also what kind of material the walls are built with. If it's just regular sheetrock with metal studs or wood studs, or it's a concrete wall. Or sometimes in the old days, they used to do this wire mesh with concrete to make it look like concrete. Mostly buildings built, I would say, the 1950s and 60s will have that design, and that blocks the signal the hell out of it, because now you have a metal mesh that you have to go through, and then you got concrete you have to go through. That concrete has sometimes little pebbles, and those pebbles also scatter the signal. It makes it more difficult. It's not the same thing when you have sheetrock that is made out of just like this white material. I forgot the name right now, but anyway, that allows the signal to go through with no problems. Glass allows the signals to go through, but not metal. So it depends on what you have. So if you have multiple floors, also you have to be careful when you do your access point. You might need access points on the second floor as well as on the first floor. Now remember of the signal pattern. Right? If you had that pattern, if you look at the pattern with an access point, some of the access points, those are squared access points they're meant for mount ceiling mount. They are meant for ceiling installation. So you put it on the ceiling, it would actually take like a beam down below to the floor, which is about 8-10 feet, something like that, and then they spread out around the room. So they make like a big circle, and that boom going forward, going straight down, is really short. So it will get to the first floor, but in the back, the signal propagation of that pattern is not meant to propagate the signal on the back of the access point. It will have some, because it will have some bleed on the back of the access point. So there is a chance that it will bleed up to the second floor, and whoever is sitting right on top of that access point on the second floor, it will receive some of that signal, but not everybody else. not the same strength that the people on the first floor. I don't know if you get the picture. So for that, you might need to have an access point also on the second floor, but never one on top of each other. Meaning that if I have a room on the first floor, I have an access point there, and then I go to the second floor, exactly in the same spot, put an access point there. What I want to is offset those two, so it's still that signal doesn't interfere with each other, because the one on the second floor is going to beam down, and even though it's like a short boom, it will hit the floor, but it will still go through the concrete and irradiate to the bottom floor. So the bottom access point will say, oh, I have an access point close to me. It might want to connect to other users. So let me back out a little bit. So this one that I see close to me, but I don't know exactly what it is, can get also users in this area. But they're not. It's on the second floor. So you see what I'm going to? So if you put in right on floor to floor, one on top of each other, they affect each other. So you need to spread them out. So usually what you want to do is put like a location where you want them, and then do a survey. Walk around. There's some devices that they sell, software that you can buy, some free devices, some free software you can have that it will do like a signal scanning. So you see the strength of the signal. They might give you like a needle or like a color to show you the strength of the signal. So if you see places that are kind of like a dead spot, then you can move your access point a little bit until you get, make sure that you cover everything. You know what's really bad? Directors or bosses or managers, they always like the corner office, and the corner office has their desk all the way in the corner. So if you put an access point in the hallway, chances are he sits so far back on that office all the way to the corner that your signal will not get to that corner. So you may have to put an access point right inside their office and irradiate the hell out of their office, because they want the corner office, and they want, because I have all this glass looking outside, they want to be able to sit all the way in the corner. But if you put the access point in the hallway, they will not get that signal. And that I've seen many times here at the college, where the directors and deans and all that, they like that corner office. So yeah, you have to look for those dead spots, and then move your access point accordingly, just to make sure that you do that. And then look at the materials, so the things are made and all that, to see how you're going to do that, to deliver that signal. Also, if there's other wireless in that area, case in point, a shopping mall where you got multiple stores with multiple Wi-Fi, then most likely what you want is just to provide Wi-Fi for your store. But if you have bleed from other stores into your area, do you want to make sure that the channels that we're using is a different channel? Remember that the channels can interfere with each other, but then that system doesn't know what channel you're using. So if they happen to have exactly the same channel, they will fight with each other. Some of the access points, most of the more enterprise type, would actually have a feature that themselves, they look at the airspace and it says, oh, look at all these channels, all of this that I see around me are using these other channels, but I see this spot here that is not being used, so I'm going to put myself in there. And since all the devices can work on any of those channels, or your phone or your laptops or your tablets and stuff like that, then you'll get to connect to that signal with no problems. So this is a good example of what not to do. It's on the book, but this is something that I would not do. If you see there's the 3 floors, and then all the devices are one on top of each other, what I just explained. So they will interfere with each other. So what I would do, I'll probably have one access point move all the way, the top one move all the way to the left, the other one to the middle, and the one to the right. And that way they don't interfere with each other. And even then, when they show this, they don't show you how big the room is. So chances are that if you put it all the way to one end, you are wasting some signal that is going into the wall or outside the building, or the walls, it's going to block it, so it's not going to go outside the building. So you might want to have those access points move towards the middle. I've seen many times friends that I go to their homes and they have their little access point on one corner of their apartment, and then they complain that when they go to the kitchen they don't get good Wi-Fi there. It's like, well, because you have it on the opposite corner, through the walls and behind the bathroom walls and all this. and the signal doesn't reach there. Another example I saw, if you go to the cafeteria at Wilson campus, that's in building 2000, first floor, there's an access point that's right next, like about 2 feet away from the huge concrete column. Well, that concrete column, I bet is so wide, and it's like about 3 feet wide, that column. That there's so much concrete and so much rebar in there that the access point is able to radiate signal to that side of the cafeteria, but anybody that's sitting behind that column gets blocked. So the signal has to go somewhere else and hit another wall and bounce back to go around that column and get to the user. But what happens? You get fading, you get latency, you get scattering, you get all these problems. So the signal that gets there is much less or less quality signal that you will get if the access point actually moved away from that column on another location where it'll be easier to see, or put, another access point on the other side to improve the signal behind the column. But like this example here from the book, yes, you can have one in every room, but not in that location like that. It has to be spread out so they don't interfere with each other. So the basic configuration for any Wi-Fi device is that you obviously you change your administrator password, you create your SSID to whatever name reflects your company, your services, or just your home or your home office, and you can have it broadcasted or not broadcasted. They broadcast it, yeah, everybody can see it. But if it's not broadcasted, then you have to remember exactly how the SSID it spells and how is it constructed with the capital and lowercase letters, right? You of course have to create some security options to make sure that people cannot get into your Wi-Fi for your work or your business. And also the DHCP is an option. DHCP usually for a home device, it has a built-in DHCP that works for all your workstations, and also for your wireless device. They all share the same DHCP, the same IP range, but you can create multiple ranges. In my house, I have the 10.10.100.0. This is /24, so the first 3 octets is to match. That's for the workstations, but the 10.10.120 is my Wi-Fi. So if I'm doing some testing, or I'm looking at the firewall and I see now if it's a 10.10.100 or 10.10.120, I can tell, oh, 120, that's a wireless device. If it's 10.10.100, it's something connected with a wire. So I have that distinction. So it helps me also part of the troubleshooting and to segregate the traffic, because now I can control what this wireless network or not wireless LAN can do on the wire LAN. I can completely have it wide open, which is okay for a home or small office, but for an enterprise, then I can control what things you can do. For example, if I have access to configure my router. So from the wire line, I want to be able from the wire line to be able to configure that router, but I don't want anybody from the wireless to be able to touch that router. So the router can receive communication for management from the 10.10.100, but 10.10.100 that's something, but not from the 10.10.120 that's something. Also, if someone happens to break into your network, they won't have access to everything on your network, because now you restricted what things they can do. But that's all part of your security options. So for the clients, it depends how you want to configure that. If you're doing that, the beacon will send out all the SSIDs. So your client, either by doing a probe, will receive and detect all those SSIDs that can associate to. Like I said, when you go to the mall, you see all these SSIDs, and they might have an option to do onboarding or offboarding. Offboarding means that you need to remove programs on the device in order to get permissions, or the onboarding is to install something on like an app on your device in order to be trusted. You do this mostly with laptops. You want to make sure that the laptop has antivirus, it's certain patches from Windows and all that. So with the onboarding, you make sure that you're not that foreign device that is not on your network, that you don't have no control over it. It's not going to bring in something into it. some of the protection that we do at the college is that the MDC open and the MDC student are not allowed to communicate with devices inside the college network. You can go to the web pages, to registration, to look at schedules and look at things like that, and you can do everything outside. Blackboard is hosted outside, so from those SSIDs you can go out and connect to that. Um, but on the offboarding is that I can control what you have, and I have to have permissions on that device. So it's usually done on corporate devices. So if it's a Miami-Dade owned laptop, then I can have a permission go in and it says, oh, you installed this application that I don't want in there, let me remove it. Or you can actually do a remote wipe that if the device gets lost or stolen, the next time they connect to the network, I send a signal to it and it wipes out all the information on the drive, and the laptop gets completely cleaned out. So any information that is there that belongs to the college and is critical information, then is not left out in the wild. So part of security is that you can do authentication. You authenticate the user either by the MAC address, so you can do MAC filtering. So remember that each device has a unique MAC address, so I can permit devices like that. That is not working too well. The book is a little bit off on that because what Apple is doing is that Apple generates multiple MAC addresses on each device, on the iPhones and on the iPads. So if you register with one specific MAC address, chances are when you go back in, it's going to randomize that MAC address and give you a different MAC address, and that MAC address is not registered. So that MAC registration doesn't work too well. What it works better is authentication based on username and password. That's what we use on the encrypted network, the MDC Secure, where you have to have a student account or a faculty account and put in your username and your password. That goes to Active Directory, remember, for authentication with the Windows domain controller servers. And if they have you are on that database, you get approved, and then that approval gets sent back to the wireless device, and it allows you to get in. Once you connect, you can do encryption. The book and the previous chapters, the previous editions, went heavily into all the different encryptions that you can do, but I guess it was taken out of the Network Plus, or the book just decided, the author not to include so many as it did in the previous one, but we'll cover some of them. We'll see. So the old protocol was WEP. WEP was very basic. That's the one they use at home that people ask you, oh, so what's the Wi-Fi password? And they see, your Wi-Fi name, and then you give it the password and like that. But that password can be broken into. A lot of those passwords are sent in original when you associate. They're sent on the clear. So there's softwares there that can kind of like the Wireshark that will sniff the software, looked at it, captured that, and goes, oh, here's your web key, and there you go, no protection. So there's more. There are other protocols like WPA, the Wi-Fi protected access, with it would generate keys and make it a little bit more secure. And also you have the introduction on TKIP, the temporary key integrity protocol, that improves over that web keys. So TKIP will give you message integrity, key distribution, because it generates different keys, and also provides encryption over it. We use 802.11, which is another encryption policy on our network, which is mostly what you do use on an enterprise network. Then they got WPA2. With WPA2 is a more is a stronger protection. It uses the CCMP, the counter mode with CBC, cipher block chaining, which creates more authentication and more encryption for the packets. So now for the message integrity, what it does is it identifies your sender, so it knows where if the communication is coming from the right device. If it's not, if it doesn't have the right signature, they will ignore the communication, and they will do the AES, the Advanced Encryption Standard, which comes together with the TKIP, to create encryption on the communication. This way, if it gets captured in the air, it's kind of like you going to a website that has an SSL certificate with a secure socket layer certificate that encrypts all the communication with a private key and a public key similar to that. So now your communication is completely secure. So this is more like now the enterprise when you use a radio server. Radio server is just an authentication server. It can have, it does have Active Directory in the background. So it will go into radios. Radios like the middleman. He's the one that it will do the query for you. If you pass that, then it will authenticate you. That's using a WPA Enterprise or WPA2 Enterprise security. But the radios, the remote authentication dial-in user service, this was an open source. It was from the old days of the dial-in for the dial-in communication. But of course, nowadays it's all through wire, through the Ethernet. And it will have a backend that authenticate the user, and all the communication is handled through EAP. So EAP is extensible authentication protocol that provides that encrypted authentication for the client and the server, so you can get into your network. So that's what we use at the college for MDC Secure, where you have to provide a username and password. It's all WPA2 and doing EAP in the background. So we are using radios. What it does is a radio creates a tunnel to your access point, right? Or in this case, the authenticator is your access point. It receives the information from your laptop, and you send everything encrypted over like a tunnel, a secure tunnel, to the radio server. So that communication is only known between the access point and your radio server. In this case, the authentication server. So those passwords and the users and everything and the SSID that you use and everything is encrypted and protected. Now, to configure a enterprise wireless, it's a pain because there's so many options. It's like an option that branches out in 2 or 3 options, and those 2 or 3 options can branches out in 2 or 3 options, and then at the end you end up with another section that has also some options, and so and all this needs to match. If they don't match correctly, then your users cannot connect. Some of the security, your AP and antenna placement. Do you want your signal to leak out outside the building? You want to leak out into other departments that they don't want to connect there. So that's where the placement goes. Geofencing, it's a geographical fencing. Like if you want something to be only contained in a certain area. Case in point, if you want wireless from your phone to be able to clock in and out from your job, for your time clock. You don't want people to be able to clock in and out from your parking lot. They're not just going to go to the parking lot and goes, okay, I'm here. And then by the time it takes me to get into the building and get my coffee cup and get all this, and then it starts to work like about a half hour later, or the same thing when they leave. They get all the things ready, start walking, and they walk to the car, and then from there. So you don't want that. So you want, let's say, for that clock in and out to be in a very close area and limit to a specific geolocation. So that can be done, through the wireless. You can have the wireless client isolation. That if something happens with that client that you don't trust it, you can isolate that client. In a way, we kind of do that with the MDC Open. MDC Open, when you connect to that, you're isolated from the college. You're nothing to do inside. So anybody can bring a laptop, a phone, a tablet, or anything, connect to that. All you need to do is to put something that reassembles an email address. You accept the terms. So we're protecting ourselves there in a way that if something happens and we know that you did something from that device, there's a terms there. There's a whole things there that nobody reads, but you accept the terms. By clicking here, you're accepting the terms of everything that's here below. So when you accept the terms, you're liable for all those things. So you got to be careful, but at least some kind of protection. You can have a captive portal. That's what we have. The captive portal is the one that takes you there. It tells you, hey, you're welcome to Miami-Dade. This is the type of network you have. This is how you get in. We're going to be changing that soon to more like avoid that email address. Yeah, email address is just useless. If you put your real email address, fine, thank you. That's good because we can have that on records. But anybody can put anything they want. So in a way, it's just pointless. But what we want is people to accept those terms. When you go to McDonald's or any of those places, Starbucks, when you connect, all you need to do is to say, yeah, I accept the terms. And you get connected. But accepting the terms, it says, hey, I'm capturing everything that you're doing. I'm saving everything that you're doing. And I'm decrypting everything that you're doing. Do you read that? If they have that on their acceptance, it means that if you connect to your corporate network or you connect to your bank and they're able to capture that information and save it, you don't know that. But everybody goes and accept that and connects to a network. So you have to be careful when you go to those places. But that's what the captive portal is for. And then the IoT access consideration is it's a headache for networks because now you have devices that don't really comply with a lot of things. They cannot get into a captive portal. They cannot get into a guest network. They cannot go automatically and accept the terms. So most likely what you have to do is to create different networks for the IoT devices so you can connect to IoT and then have those devices that don't obey a lot of the rules and they're very basic devices that can connect to your network. And then do you really want those things on your network? It's like if the devices, if you're really paranoid and say, oh, those devices are made in China and they are trying to collect information about your network around it, even though it's an IoT device, they might be collecting data from everything that they see around or everything over the air and ship it to China and then have them, inspect it and then try to see if you are worth it to be broken into and get the data from your network. So it's a risk. So my IoT devices that I have at home, I monitor the communication to make sure that the communication is with the United States. So I apply the geofencing. If it's trying to go to China, Russia, or any of those places, that communication is being blocked. So my 10.10.120.0 network is not allowed to go to a lot of countries. It's just blocked to apply geofencing to any device that connects to my network. Now, the author loves to throw this in there because he's been in the past 3 releases of the book and now he still have it. Oh, but he takes out cellular communication and satellite communication. But anyway, but ward driving is, when people drive around to see if you have an open wireless or something like that. Ward chalking, it's that they put a mark on your sidewalk to say when there's an open AP. How I think Comcast is the one that has that. I think it's Xfinity SSID that they said that now they have thousands of hotspots around the country because they use your home network to be a hotspot for anyone that goes around your neighborhood or somebody that goes next door to you and they can connect to that network. AT&T does the same thing. The first thing I do is log into those access points or those routers and disable that guest network. I don't want anybody using my network, although they don't charge you for it. It's not that if they use bandwidth that they're going to charge you for it because they don't, but it's just the fact that they're using my device to communicate out and I don't know who they are, and my provider saying, oh, it's okay that my customers are just wanting to give some options and you can have that option too. It's like, no, I'm not going to connect to anybody else's network like that, and I don't want anybody to use my network. But it's just to show if someone has an open network. Evil twin is when you have one network that it mimics yours. It happened to us one time. I was in building 9 and I see an MDC secure SSID, and I see it with lowercase s. And if you notice, it's made with uppercase s. So they were both showing up, the MDC capital S for secure, and then MDC dash lowercase s for secure. And I was like, oh, I configured something wrong on my network because it shouldn't be two like that. Well, long story short, at one of the labs in building 9000 from NTech Labs, one of the lab technicians, one of the part-timers, decided to put his own access point in there, and he put MDC secure. Now, The flaw here is that you cannot mimic my network. I have some official wireless networks at the college and official names that we are using, and you cannot evil twin that one, because now someone trying might, but I don't know what they were doing. But if you mimic the authentication page, now you can capture the username and the password of the user trying to connect to that network. And I reported to the department right away, and actually I went myself and I unplugged it, went to the dean and said, here, I unplugged this from this room, it's doing this, is an evil twin of the MDC secure, and we don't want this on our network. They cannot have it here. So I don't know what happened to that, but I did my I did my part. But yeah, it can happen for someone that wants to steal the credentials. WPA attack is WPA cracking is one of those stations that has special software, and it tries to crack into those WPA keys or WPS keys. Also, WPS is also a feature that they put on some access points that it has like a pin number. So you press that and go to your device, press the WPS, and then you put that pin. They all talk to each other. They send the AP information for the SSIDs, the passwords, and everything. But that's very insecure. And when you have a pin code, even if you have 4 digits, 10,000 numbers for networks is nothing. You can do that in a matter of seconds. You can send so much data across that you can brute force and get in, unless you make it 16 characters. Now we're talking, but they're not. They're like 3 or 4 characters. So that pin code is really not too secure. In my network, the access point provided by AT&T has the WPS disabled. And then to troubleshoot, you can have some tools. So you have your spectrum analyzer, a device that just registers the signals. The college we use a product called Ikahow. Ikahow is a device that they sell you the software, and they sell you the license, and they sell you the proprietary network cards. When you put that, it will analyze the Wi-Fi. You can walk around. You have the floor plan. It will do test points, so it can give you a mapping of what signal you get in every area. And it will also, with a wireless analyzer, you can see what networks are available, what's out there, what's the signal, what strength, are they fighting with the same channel, or you might see how they change channels when you see, MDC secure, and you see it 4 times, but it's coming from 4 different signals, but one stronger than another, is because you might have 4 access points broadcasting the same, doing that beacon with the same signal, the same SSID, propagating that. Announcing that it has it, but one is stronger than the other one. So of course, my device will probably connect, most likely, and by design, it will connect to the one with the strongest signal. But you can see that with a wireless analyzer. So some of these tools analyze the access points, the stations, the channels. It will measure the signal. It will say that any signal loss, any noise. It will give you all the information. There's a few that I use. There's one company called Ubiquiti. Ubiquiti has a utility that is a free utility for your phone. You can download it and make that into a small wireless analyzer. Remember, your phone is a multi-radio device. It has your telephony radio, which communicates for your voice calls. It has your data radio, that's the one that communicates with the with your provider tower for data communication and internet. And also you have the Wi-Fi radio, which is for you to communicate with an internal Wi-Fi network. When you connect to a Wi-Fi network, all your data goes through that. It prefers to go to all your data. All data communication will prefer to go through your Wi-Fi communication. If that is not available, it will go through your data communication, your data radio. And then you don't have any of those two. All you have is voice calls, right? You cannot you can only make phone calls. Also, when you connect to the Wi-Fi, some devices now has Wi-Fi calling. So even though you might not get signal from your tower for your telephony radio, the phone is able to make the communication through your Wi-Fi if you have a good Wi-Fi communication and get a perfect call, even though your telephony radio is not receiving a good signal. So it will roll over to the Wi-Fi, goes, oh, let me turn on Wi-Fi calling. And that depends, it's features on your phone itself. It's not features on your provider. It's actually features on your phone if your phone is able to do that. But some of these tools allow you to capture. You can measure the throughput. You can do a throughput test and see how much data you can transmit, and if you get any errors. And then you can analyze multiple channels. I'll show one of those in class. I'll see if I can project my my phone to the class so you can see how do they look like. So some of the pitfalls you can have, it happens, the wrong SSID. Like I said, when I saw that one with the lowercase s and it was supposed to be uppercase s, it scared me because, oh my God, I made a mistake because I shouldn't have had that. It was just, it was something else in there. But I'm careful with those things. You have to be careful with that. Encryption, like I said, encryption is touchy because encryption is options over options over options. So you have to make sure that you have the proper options to make sure and see that guarantee that encryption is going to work. If you have a passphrase, make sure the passphrase is correct. The channel utilization, make sure that you propagate those channels, allow the devices to pick the channels. The RF frequencies, I mentioned, like an example is those phones that are made for Verizon but not for T-Mobile, or it might work towards AT&T, or no, it depends what radio frequencies they match. Nowadays, remember, all the Wi-Fi was on 2.4 gigahertz, 5 gigahertz, and now it's going to the 6 gigahertz, 6 point something. So there are some devices, older devices, that they don't require a lot of communication. Some of those IoT devices are some small home devices, so they don't support 5. They only support 2.4 gigahertz. So you have to make sure that your 2.4 radio is turned on. I did try to turn it off at my house, and then I realized that one of my phones that I have, one of the phones I use for like a backup phone, it did not support 5 gigahertz. So I could not connect Wi-Fi to that. It could not download updates. It could not do a whole bunch of things. And a lot of stuff that communicate through data, it would try to use the data plan because it could not connect through my Wi-Fi at home, and I didn't want to use my data plan. Mismatch standards. Make sure that all the standards are correct. Like I said, there are all kinds of different standards. So you have to lay down what you want and what you need, and with the devices you'll be working with. IoT devices. At the college we have a problem because we don't know what devices you're bringing in. We don't know if you came from South America, you're an international student, and you bought a phone that is not supported here, or frequencies that are not supported. It might be an older phone that uses only 2.4 gigahertz, so we have to keep the 2.4 turned on. We cannot turn it off because devices like that. And then the long AP association time is just like devices that stay on for too long. Yeah, if you have a temperature sensor or a thermostat, that IoT that connects to your wireless, then you expect those to be there for a long time. But you also have to monitor those things and just make sure that no one left the device behind collecting data on your network and see what it sees on the Wi-Fi. Case in point, one of the protections that we have on the open and the student is that we're not allowed a peer-to-peer communication. So if you have two devices on the same SSID and you want to send data, or you want to retrieve data from another one or send files across, it's not allowed. We prohibit that. You're connecting there to get out to the internet, do your things, but gaming is one of those things that, because of this, it doesn't work. When you go to MDC Secure, which allows the peer-to-peer communication, now you can have two wireless devices and send data across files, share files through the wireless with no problems. But it's some of the protection that you put into your wireless. So more other things that you can have: insufficient wireless coverage. Remember, like the corner office with the boss sitting right in the corner with his view to the outside, the parking lot or the mountain or whatever. Well, there's no mountains in Miami, but you can look at the ocean, at the bay. Then he might not get coverage, so I have to be careful for that. Any attenuation or signal loss due to a construction, the walls, things are into your area, so you have to look at the position of the access point. Interference from other devices, like I said, any electrical, microwaves and things like that will create that. Any other access points from other areas or other departments might affect you. That will create this channel overlap too. That they interfere with each other. The wireless standards, make sure they're using, the standards. Simultaneous wire wireless connections. It happens a lot. People bring in the laptop, professors or students, and they'll plug into a wire. They forget that the wireless is turned on, so now your device is kind of confused because Windows is not smart enough to say, hey, I can use only the wire. The wire is preferred over the wireless because the wire is giving me a 1 gig connection, but the wireless is only giving me, I don't know, 100 megs of throughput or 200 megs of throughput. So the two connections sometimes creates problems. It will create it could have some asymmetric routing that it goes one way and it comes back the other. You try to avoid that. If you have a wireless connection, keep on the wireless. Once you connect the wire, disable your wireless so you don't have the dual IPs and dual connections. Firmware updates, like on anything with computers, you have to make sure you have the right firmware updates on your devices, your wireless access points, your wireless controllers, your switches, your routers, and everything, your phones, your tablets, your laptops, everything. Incorrect antenna type, yeah, if you don't have omnidirectional and you put a directional antenna, of course the direction is going to just point in one direction, and if you happen to be offset to the side, it's not going to work. Antenna polarization is a good point. Polarization, the antenna has a polarization. Do you remember, I don't know if you've seen, in the old days they used to show like a radio antenna, and they draw these circles around it when it's propagating the signal, right? Those circles were on the same plane, right? On the same plane, they said on the X plane. So it's the old, expanded across. Like if you throw a rock into a lake, that it starts expanding that way. Well, imagine that's a polarization on one way. So to receive the signal, that signal, which wire will get a better signal? The one that is standing horizontal, or the one that is standing vertical? If you see the circles that go across like that on the X-plane, you want an antenna that is actually horizontal. So when the wave hits that horizontal wire, it gets more area to receive the signal. If you have it standing up and the signal comes, it's just a little hits on the signal. So that's why I talk about polarization. So sometimes those rabbit ear antennas, you have to move them one like an inclination or straight or down or something until you get the right polarization, because that also throws signals on one polarization. I can show that in class how the polarization works, because it's pretty interesting that you have the right. And that's why when I said the laptop screen, if you tilt it a little bit, now you're changing that polarization, because now it's not fully straight. The antenna is not like a circle standing up, but it's a circle that is a 45 degrees. So that might be able to catch a better signal, because antenna is propagating the signal on an angle, and then now the antenna is on the same angle and it will receive it better. Client saturation over capacity. Yes, if you have too many clients, it cannot handle it. There's too much communication, too much, the MIMO, the multiple in, multiple out. There's just too many at the same time. So you have to use those mechanisms to back off, and wait until the channel is free so for anybody to use it. So when you got too many of those waiting, then your chances of getting the channel they're slim. So it creates problems. Client dissociation issues, it happens. Sometimes clients start to connect and disconnect. Apple devices like to do that. Apple devices wants to save power. So after a few seconds or not using your Wi-Fi, the Wi-Fi will turn off. And when you get it, it will automatically turn back on. But then what happens, if it turns off and it stays off long enough, your access point might dissociate, because that client disappeared. I don't see it anymore. It has been 3 minutes, 5 minutes, 6 minutes, time out. So I'll deassociate that device. So when you try to use your laptop again, or your Apple laptop or your Apple tablet, the radio turns on and tries to reestablish that communication they had before, but it's already gone. So you had to reconnect again. If it's an automatic association, then it had to reassociate, but it introduces delays, and the people are going to say, oh, your wireless is so slow. Well, no, it's not. It's your device that keeps going on and off, and I have no control over that. So it happens. Oh, by the way, there's a setting which is called the sleeping client. that you can set up a timer. They said, okay, don't wait just 5 or 6 minutes, wait 20 minutes, wait half an hour, wait an hour. If that device come back within an hour, then take him again and don't ask him for passwords or identification again, because just hold it for those devices, for all the devices. So if they disappear and they happen to come back within that half an hour or 1 hour, then accept them again, so you have to reconnect again. And that's the problem that we had with the Apple devices, and it's called sleeping clients. Nowadays, I think Android is doing the same thing, that after a certain amount of time, it will turn off the radio to save power. It's just a feature to save power in your device. But the moment you need it back, then it might be too late, and you have to reconnect again. So it's, two sides: the device themselves and your controller, your access points, be able to deal with these associations that happens constantly. And that's the end of module 6. So we covered the wireless, the standards, how to plan, how to secure your network, how to troubleshoot it. Like I said, the previous versions of the book went way deeper into the encryption and all the different methods that you can have to encrypt the data on Wi-Fi. But I think there's another chapter later on to how to encrypt the data on Ethernet. For remote connection and things like that. So I guess they leverage that part on what they use on Wi-Fi. I'm kind of disappointed that they took out the satellite communication, because that explains also a little bit how the whole radio propagation goes, and the same thing with the cellular communication, because cellulars, they do have a wireless in there, and how they interact with the system. But anyway, the choice of the author, or I guess something that was taken out of Network Plus, but I'll cover some of that in class, so at least you're familiar with it. All right, thank you very much.